soon as it comes on. I've got several computers to turn on my own. Okay. So this last thing, real numbers can be, the real number, representations by decimals probably. We can also represent real numbers by any other base. Like in computers, we use base 2 and base 16 to put in numbers. You may not, but the computer does. It's what it works with internally. We can use base 3, for example. So in base 3, for example, 1/3 would be 0.1. Because in base 3, each thing is how many thirds or ninths or 27ths or whatever. So 0.01 in base 3 would be 1/9, as an example. Got one more person coming in. So welcome, Kenzie. Anyway, but we can also represent numbers by continued fractions. We might talk about that sometime. Sometimes people have trouble doing these fractional things. And what I would say here, when I see this, what I would do is make a common denominator in both of these and do the same common denominator and then flip this one over when you're done. Okay. One of the problems here is that people have trouble, they cancel, and you can only cancel multiply. This is a plus. You're not allowed to cancel something common. You're supposed to know that, but people mess that up. We're dealing with all negatives gives people trouble. You got to know how to manipulate stuff like that. Anyway, and here I find that some students who are used to using calculators, if you have to multiply 24 times 76 over 16 times 27, which, by the way, I would do in my head, and I hope you can, I would never multiply 24 times 76 in my head and multiply 16 times 27 in my head and then divide. What I would do is factor. If you can factor things, you're much more likely to do the problem correctly. When you deal with big numbers, you're much less familiar with them, so you won't know when you're wrong. When you multiply 9 times 6, I hope you know what the number is that you're supposed to get. But when you do 95 times 27, you might not know immediately. Now, if there are tricks to doing numbers, for example, I mean, I can do some things that actually make it look like I'm really smart, but what I know is a lot of tricks. And so I can, one more person coming in, I can trick people into thinking that I know more than I do just because I know some ways to manipulate things. Like 14 times 16, for example, is 224, which I just know because I know what 15 plus 1 times 15 minus 1 is, 225 minus 1. So anyway, there's a lot of things like that that will help you do things easier and make less mistakes. But anyway, I just put this up for people who came early to give you something to do. I'll do one more little thing here, then we'll get to what I want to do today, which is something else. Just some things for you to think about. Sometimes people have trouble with manipulating numbers around in fractions. So I can write this as 4 times 1/7. I can write it as 4 over 7. I can write it as 1/7 times 4 by turning this around. I can change the 4 to 4 over 1 because actually, when you multiply these things, they're both supposed to be fractions. But we sometimes slip in and slip out of different number systems without even knowing it. But a number like 4 pi, if you think about it, that is not a number in the same sense. Pi is a name for a number. Now 4 is a name for a number also, but it's much more familiar. So when I say 4 times 2, you know the answer is 8. If I say 4 times pi, the answer is 4 times pi. You don't know what the numerical answer is because we never do the computation. We leave it undone. We leave it as 4 pi. Okay, you don't leave 4 times 2 undone probably. We say simplify. 4 pi is already simple. And we can't write it down exactly. If you change pi to 3.1415925 and so on, whatever, you still don't get the exact number then. So I don't approximate in this class unless I know that I'm supposed to approximate. We'll talk about that later. Some people think this next thing I'm writing here is always true. Now, what you've got to get used to in this kind of class is knowing what the hypotheses are. What are we assuming here? And most people, when they see letters, assume they're positive. But if you go over here, I have 1. The square root of 1 is 1. But I can write 1 as -1 times -1. And if I use this rule over here, I will get I times I. And I times I is -1 because I had to go into complex numbers to do it. The point is, we just got 1 as -1. And that's because we used a rule which is not always a rule. It's only a rule if both of these are real numbers greater than or equal to 0. And what a lot of times people do is they forget the hypotheses. They forget the if part. And one of the things we're going to study today in a few minutes is about if-then sentences. Okay, some people have trouble with 8 to the 2/3 power. Now, what I would never do is multiply 8 squared first and then try to find the cube root of 64. What I would rather do is find the cube root of 8, which is 2, and then square it. One's much easier than the other. What you want to do when you do stuff is think. Figure out what you ought to do. Now, what about -8 to the 1/3? -2. -2 times -2 times -2 is -1/8, is -8. What about -8 to the 4/12?
You would take it to the 4th, then do it to 12th. That way you get with negatives. That way you don't have to do the complex
The first
one.
answer is negative, and if you do this one, it's positive. Because if you raise -8 to the 4th power, it's positive, and the 12th root of a positive number is positive. But the point is, you never do this. If you see this, you say the problem's not stated correctly, because we only do fractional powers when the number is in reduced form. Unless it's positive. If it's positive, doesn't matter. But if it's negative, if you get 4/12 here and you carry out those two things like on a calculator, it may give you the wrong answer. So the rule is you reduce, if you want to do this problem, fine. But if somebody gives you this problem, it's not correctly written down. I would say I'm not going to do that problem because I look at that and I know they're trying to trick me. They're trying to make me look stupid because I'm going to come up with two different answers. And they're going to say, oh, look what you did. Anyway, okay. For example, just some quick little dumb things. There's no subtraction in the whole numbers. When you're in a certain grade in grade school, in elementary school, you take a smaller number from a bigger number. That's called a difference. You take the difference. Now, some people say, what's the difference? Well, they mean take something less from something more. You can't take 6 from 4. If you have 6 people and 4 pieces of pizza, you got a problem. Okay? If you have 4 people and 6 pieces of pizza, you have a different problem, but at least everybody gets to eat. Okay? Now, the next year in grade school, you learn about negative numbers. And then you can take 6 from 4 because, unknown to you perhaps, you've entered a different number system. Grade school teachers don't know it's a different number system, so they teach you a bunch of rules to learn. But actually, integers have different rules. Positive and negative numbers have different rules than whole numbers. Whole numbers are not a subset of integers. They're an isomorphic set to integers. They behave the same way, but they're not identical. They are similar. We'll talk more about that later. Okay? You can't divide whole numbers either. There is no thing like 1 divided by 2 in whole numbers. You can take 4 and divide it by 2, but that turns out not to be division. That turns out to be multiplication if you think about it. If I say 8 divided by 4 is 2 and ask you why, you'll tell me that 4 times 2 is 8. It's actually giving a multiplication problem when you say 4. And so what we have is 4 divides 8, but we don't do division. Okay? And so anyway, we can talk more about these sort of things later because I want to get to some other things, but I may come back to these. I'm just trying to give you some things to think about, like do you know how to geometrically produce the number exactly 1/7 on a, suppose I know a line is this long, between my two fingers, okay? How could I get 1/7 of it exactly? Do you know how to do that? Anybody?
You could fold it 7 times.
Well, that's hard to do. Have you tried to fold a letter 3 times and put it in an envelope? Difficult to do unless you're a secretary and done it 1,000 times. Yeah, if you can do it 7 times, great. But most of us can't figure that out, and you have to keep working on it. I'm talking about exactly. Now, in a different way of thinking altogether, by the way, suppose that I take a sheet of paper and fold it once. I'll be doubling its width, right? And if I fold it again, I'll have 4 times the amount. How thick will it be if I double it 43 times?
You can't. There's no way you can fold the paper that many times.
I know that. But if you could, how thick would it be? Mathematically,
like to the moon?
mathematically, we can do it.
Yeah, it'll go up to like the moon or something. Or
A million
beyond.
or something, okay?
Yeah.
We're going to talk about a million or something in a minute. About 400,000 miles thick. So if we could do it, we wouldn't have to launch a satellite to the moon or a spacecraft. We could just climb there. And if you double that again, you'd have a return trip. Powers are very big, real fast. So let me ask you a question, and I don't want you to figure this out. I want you to just think it. How long is 1,000,000 seconds? Do you think you're 1,000,000 seconds old? I don't want you to compute it. Just what do you think? Is it days, weeks, months, years, second? I mean, how long is 1,000,000 seconds? An hour? 10 years? What do you think? Anybody have a guess? And again, don't figure it out. Just how do you feel? Anybody 1,000,000 seconds old?
I think so.
You think so?
I think so too.
Yeah, I feel like, I mean,
1,000,000
seconds on
million-
the old, so.
1,000,000 seconds is between 10 and 11 days. Which I think, if I don't know you guys yet, but I think you think that's too little. Like if I could spend $1 a second, I could spend 1,000,000 in 11 days. Now, how long is 1,000,000,000 seconds?
Like-
Isn't
Answer,
that like
15 years
like
or something.
70 plus years?
32 years.
32.
And the way people react to that, if 1,000,000 is 11 days, a little less, and 1,000,000,000 is 32 years, 1,000,000,000 is much bigger than you thought it was. It doesn't seem like 11 days ought to go to 32 years just by multiplying by 1,000, but it does. Now, we just gave the country $9 trillion. How long would it take us to spend that money at $1 a second?
Well,
1,000,000,000,000 years is 1,000 times 32,000 years.
I think more than that time than we
I'm,
need.
I'm sorry, it's 32,000 years. So 9 of those, it would take a long, long time. Now, my point is, I don't think anybody in Congress, and this is not a political statement, I don't think anybody in Congress understands the difference between 1,000,000, 1,000,000,000, and 1,000,000,000,000, because all you have to do is change the first couple of letters, okay? And so they toss these numbers around like, oh, well, let's give them $1 billion to somebody. Oh, no, let's make it 1,000,000,000,000. And they just sort of just say that and they vote on it. And I don't think they know what they're doing to us tax-wise for the next 50 years. Okay, now I'm not saying I don't support such things. I'm not talking politically at all. What I'm saying is, I don't think the people who are in charge have any clue as to the size of the numbers they're talking about. Okay, what do you think? You agree?
I mean, you have to know half the people who are on top are more than all millionaires. So, yeah.
Yeah, but big numbers are things we don't understand very well, okay? And small numbers we don't understand very well either. So we approximate them and we do other things with them. Anyway, enough about that. So I want to change the screen here and figure out how to do that. And I will get better at that all the time. But I'm going to change the screen to something else I want to talk about. Here it is. No, I don't want to do that. I want to do this one. Okay, what you should see on the screen now is deductive logic, and you can make that bigger if you need to. I'm going to make it bigger for me. Now, I hope you have started reading this. This is in your, just looking to see how many people we got here today. We got everybody, I think. Yes, but I didn't admit everybody. So how'd you get in? That must have sneaked in. Okay. Anyway, we got everybody. So let me take a snapshot of the picture I have here. And that way we'll take attendance. And I can do that again. I just got to get back to seeing how to do these crazy things. I need to take a picture of the window. And so it tells me to just a second. It says I took a picture of the window. So good. So that gets your attendance taken for the day. So great. Okay. So enough of that. But I need to do that every day. I may just do that without telling you sometime, just sort of flipping it around. But if you see this on the screen, this is in Blackboard. I hope you can either download it or read it on the screen. And let me ask you about that. Do you want ever stuff to be hard copy, or are you able to do that yourself?
I think online would be easier since most of us don't really have access to a printer and we have to pay 30 cents to print it easily.
Okay.
If I recall correctly, the honor students get free access to printing.
Yeah, but that's only the honors students. So anybody who's not is kind of gotta go pay for that.
Okay. You guys know stuff I don't know. So
everyone here should be an honor student.
Yeah.
Oh, wait, is
Yeah.
it an honors student?
If you're in the honors class, you're an honor student. So
I'm in the honors class, but is everybody too?
I'm pretty sure you're an honor student. They'll let you
Oh.
print it. Just tell them you're taking an honors class.
Okay.
If anybody's not an honor student, the Office of Diversity and Inclusion also has a few pages of free printing a day. I think it's like 10 a day.
Okay, well, this is all good stuff. So you guys keep communicating like this and stuff. I don't mean while I'm talking, but we need to make sure everybody gets as much out of the things as they can. Okay, now, did you notice that I put a link on your computer on Blackboard to do the videos? And so there's a Zoom session thing, and the videos are there yesterday. Now, at the moment, in one folder, just because we're having a lot of people do this, in the folder right now is a video for Calc 3 as well. Later, I may separate the folders, but right now you could look at the Calc 3 video if you wanted to. I don't see any harm in that. I don't see any why you do it either. But I just want to make it simpler for the person that's transmitting these videos so they don't have to remember which class to go to. So right now you'll see two videos from yesterday. And I looked at them, they're not very good. I mean, because I looked at myself and I thought, boy, you don't want to look at these things. But anyway, okay. I'm assuming you can read. And so, as I say, if you want to make a hard copy, you can do that. While we do that, I'm going to go through some of this today. I'm not going to go through the first pages. This is just kind of motivation. But the second page here, what we're trying to do with logic, with mathematical logic, is take things we say in words. Like if I say X is a real number, what we like to do is put it into symbols because we want to make sure we all interpret it the same way. And once we get it symbolically, the symbols only have usually one meaning. So here's a sentence, and maybe you've read all this and maybe you know all about this, but I'm going to go through it and not go through all these paragraphs if you can see my cursor moving around. But suppose we have a statement, either Joe is at work or Joe is at home. Joe is not at work, therefore Joe is at home. This is called an argument. The first two things, 1 and 2, are called premises or hypotheses. The third thing is called a conclusion. And when you do something simple like this, the word therefore usually tells you what the conclusion is. It's the last thing. And this is an argument, okay? And what we're supposed to do is draw some knowledge from what the sentences say, okay? And I see somebody says, remember this stuff, that's good. We'll maybe get beyond what you remember in a little bit by the time we get to page 30, but we'll see. Anyway, how will we symbolize that? Well, it turns out mathematically, you can get by in all of mathematics with 2 words, 3 words really, not the word or, and the word and, okay? And then 2 quantifiers, which we'll get to. But there's only 5 things that all mathematical statements are made of: or, and not, and the quantifiers, which we'll talk about later. Okay, so what we try to do is take the first sentence here, because this is called a compound sentence, because it's got 2 parts. We take Joe is at work. The either or is really the same word. I didn't have to say either at all, but I said it just because we say it in English sometimes. But Joe is at work, if we call that sentence P, and Joe is at home, sentence Q, and we leave the R alone, then we can say P or Q. As long as we know what P is and what Q is, we can say that and people would understand it. The Joe is not at work, the not, notice in English, is in the middle. Well, we could say it's not the case that Joe is at work. That's not P. And what can you conclude from that? Most of us, I think, without knowing much about logic, would conclude the last statement that Joe is home. Okay? Now, this is a valid argument form. There are 9 for us. It's more complicated, but I'm simplifying it. There's 9 argument forms that people use when they talk to each other. And this is called disjunctive syllogism. Now, I'm not going to test you over such stuff, but basically there's 9 of these, and this is one of them, and it's a structure. And whenever you have this structure in a proof in math, you can draw this conclusion Q if you have these 2 things you know. So now I change it a little bit. Let P be the statement Joe has the money, and Q be the statement Joe can pay his bills. So the first sentence here would be, if Joe has the money, then Joe can pay his bills. The second statement says Joe does have the money. So what do you conclude? Joe can pay his bills. Okay? This is called modus ponens. It's Latin, and it means the way that affirms by affirming. It comes from 2,000 years ago. It's also called the law of detachment. Again, none of this stuff you're going to be tested over. I'm just doing this because I think you might like to know. The sentence with an if-then in it is called conditional. It's also called a material implication. I don't think I said that. If you want to get all highfalutin and sound like you know something, you can call the first part the antecedent and the second part the consequent. And we can get all technical about all this, but we're not going to. We're just going to use this stuff every day, but not use all these fancy names. Anyway, here's the symbolization of it, and fine. This one is called modus tollens. And this says, if Joe has the money, Joe can pay his bills. Joe can't pay his bills, therefore, Joe doesn't have the money. And when you symbolize that, that's if P then Q, not Q, therefore not P. We will use that a lot also. Okay? This modus ponens and the modus tollens are the most useful things we use in logic. And so on. Now, this one is invalid. Okay. We're going to get into validity. When we have an argument, we classify an argument as valid or invalid. We'll get into that a little bit later in the notes. A valid argument is what you use in a law court, for example. And you use 2 things if you're an attorney that's prosecuting a case. One, you put forth facts as evidence, and each thing you say is supposed to be true. And you have a logical structure called a valid argument, so that if all the hypotheses are true, the conclusion must be true. Now, a defense attorney who's trying to mess up the case is either going to try to show that some hypothesis is not true and therefore you don't have to believe the thing, or that the structure is wrong, even if all the hypotheses are true. Okay? But what we want for a valid argument is a structure that's okay, and we also want to have true premises, true hypotheses. And if that's the case, then you can believe the conclusion. Now, none of these things should be inside the mathematics. We'll talk about that in a little bit. When I classify something as true or false, that shouldn't be part of the statement. For example, suppose I tell you right now I am lying. Am I telling you the truth? Suppose I'm a barber of a small town and I shave every man who does not shave himself. The question is, who shaves the barber? Because if I shave everybody who doesn't shave himself, then if I don't shave myself, I do, and if I do shave myself, I don't.
I've heard that one before, and it works if the barber is a woman.
Yeah. Now, the point is, fortunately, in math, we do not allow such statements. If you've ever picked up a manual, a computer, sometimes you'll see a page that says, this page is left blank. And that's a lie, because it has those words on it. Okay? So when you judge something as true or false, that has to be outside the system. You judge the system, the thing that's written, from outside. You don't put it inside. Okay, now sometimes we do, that's called meta mathematics. We'll get into that a little bit later too. Anyway, if you go down through here, and we don't have time during the class to do all these things, but I hope you do when you read them, you'll find out there's 9 of these. And some of them, are kind of obvious. Some of them aren't. Some of them politicians use wrongly. And if you're not listening carefully, they'll get by with something that they shouldn't. For example, some people will say P, therefore P or Q. That's not valid. Or is it? Well, that might be. What about P, therefore P and Q? Now, you ought to know the difference between or and. We're going to define those in a little bit mathematically, so we know what the mathematics means when we use or and. For example, we get in confusion, you have divorces and stuff over things like, if I come to see, well, let's say, are you going to come to see me today or not? How do you answer that? Does yes mean you're coming, or yes mean you're not coming?
I mean, yes, I'm coming, but no, I'm not coming.
Right, but if you just say one, either say yes or no, there's no way the person you answered knows what you meant.
Yeah, because it could be, yes, I'm not coming, or no, I'm not coming.
Well, yeah, because you're trying to clarify a stupid question, okay? You're trying to clarify the person without telling them they're dumb, but they should have said it better. They should have just said, are you coming home? If they say, are you coming home or not? That's a tautology. The answer is, I don't know, whatever. So it's not a tautology. I shouldn't have said it. What? Oh, okay. I laughed because I just had Siri on my iPhone try to answer the question. And I thought I had my phone turned off. Okay. I don't know if you heard that or not, but Siri tried to answer my question. Okay. So we're going to learn about or and and. Now, if I said to you, in the restaurant, you can have meat or potatoes, can you have both in the menu item?
No.
And that's called an exclusive or. Okay. But if I said some other way of saying or, you might include either one. Like if I have 2 statements, like we had Joe is at home or Joe is at work, if either one of those is true, we would say the whole sentence is true. And that's this one right here. If we know something or the other. This is the inclusive or, not the exclusive or. We'll get into that more. But this is not correct. Okay? And politicians like this one. A politician likes to say P or Q and then try to get you to believe P. In other words, P is false and Q is true, and they try to go to the P one that's false. You might think through some of the speeches you've heard. Anyway, we have all kinds of these things. And so I want you to read through this. And then I have a page here a little further on 6, just a review of English. Okay. What is a declarative sentence? What's an interrogative sentence and all that? First in math, for example, we don't have imperative sentences very often. Like if I say 4, I'm not talking about golf. Because when somebody says 4, that's an imperative. They're warning you the ball's going to hit you in the head. If you think about it, if you know anything about golf. Anyway, so that's a page about English. And then we get into the actual meat of stuff where we start talking about building these sentences. And in the middle here is where I talk about 2 languages, a source language and an object language. We actually write math in an object language, but we always deal with it in a source language because we talk about it. And you'll have to know which language you're in. In other words, are we talking about the object itself? Or are we talking about whether the object is true or not? And sometimes you can get confused. For example, if I say to you, and what I'm going to say to you will sound wrong for a while, and then all of a sudden it'll be okay. 3 plus 4 is 9 is false. And if you think about that, the first part made you think, what's he saying? And then I said it's false, and that's okay. Okay. Now that should not appear in an object statement. That should only appear in a source statement because we're trying to judge something. The word false should not actually be in the mathematics itself. Okay. Well, you can read about this stuff, and maybe you'll have, if you haven't studied it yet, you need to study it, not read it more than read it more than once. But what people started doing, and this is around 1914, they started learning that they couldn't rely on their intuition. From about 1870 on in mathematical circles, a lot of things were false. And so in order to try to figure out what was true and what wasn't, they needed to develop what's called mathematical logic. And by 1914, somebody, and there's arguments about, it's like who had the first airplane or something. There's arguments about different concepts, including who had the first idea I'm going to tell you about. The idea here was to use what's called a truth table to tell you what something means. And that was done about 1914 for the very first time, but 2 or 3 people say they did it first. And of course, they're all dead now, so nobody cares. But for a while in the 1920s, there was a big argument in math circles as to who did it first. Who cares? But as I say, sometimes people did. So we're going to start symbolizing things. If P is a statement, and all that is a complete English sentence, I have a period, and I have a verb, and an object, and a subject, and all that. Then we're going to, when we put a little squiggle in front of it, it's, well, McKinley is saying something to you guys. I'm not paying attention to that, but maybe I should. McKinley, should I know what you're saying, or do you, does it matter right now? Anyway, no, thank you. Okay, so not this is read not P. Okay, and the negation of P. Now that doesn't tell you what it means. It tells you what you're trying to tell people about. Okay. Now, down here we have what's called a truth table. Now, a P can either be a true statement or a false statement. All statements in math are either true or false. We do not admit any statement into a mathematical context which is both or neither. So every statement we deal with will be true or false. That doesn't mean you know which it is, but you know it is one of them. Okay? Or we don't use it. English is much more complicated than that, but math is relatively simple that way. So what we do is we put rows in for when I'm in row 1, I'm assuming P is true. When I put in row 2, I'm assuming P is false. And the question is, what is the meaning of not P when P is true? Now, I said that wrong. I said it on purpose, but I said it wrong. I don't really care what the meaning of the statement is. I care about whether it's true or false. So I don't care what the statement says, but if I assume it's true, then if I put a squiggle in front of it, that's saying it's false. Not P is false when P is true. And not P is true when P is false. It's a very simple idea. Okay, so we have a statement. If you know the statement is true or false, you know what not P is. It's the opposite. And that's the simplest one. This is the only what we call a unary conjunctive. And it's only got one thing. Now, what this paragraph is talking about is if you have two statements together, like we had Joe with two different statements a while ago, then we list one as P and one as Q, and then we're going to have four things in the truth table. And so when you see a truth table with P and Q in it, it's going to have four rows. And what we try to do is all do it the same way, because you can mix these things around. So we always take the most inside one and do a true, false, true, false. The outside one, we do two truths and two falses. And that way, everybody has the same truth table.
Hey,
If I only have- I'm sorry.
this the same thing as binary? Like the binary truth table?
This is unary, and this is binary.
Okay. I was about to say, isn't this binary truth tables?
Binary means two.
Yeah.
In the truth table, there's four rows.
Okay.
It's and will be called a binary connective, whereas not is called a unary connective. Okay. Some people say conjunction, but it's more correct to say connective. Anyway, what does this statement say? It says not P. And what's this? This I haven't talked about before. This is equivalent. This is going to mean same truth table. And in math, if we have equivalent statements, we can replace one by the other, because all we really care about is whether they're both true or both false. So if I still have one statement and I put two negations in front of it, called a double negation, that gives you back the same truth table as you had originally. So if you build this truth table, here's the original, and these right now are blank. One of the problems with this is once you fill a truth table out, you can't find out how you did it. So think of these four letters right here as not being there for a minute. So you draw your lines, you put your P there and your true false, and now I got to figure this out. So the whole statement is straight across there. What you do is go to the most inside and figure out what this is based on which row you're in. So not P here, if I'm in row one, this would be false. So I fill that in. Okay, then I fill this one in because now P is false, so I fill this one in. Is that making sense?
Hey, Dr. Brady.
So, I'm sorry?
Dr. Brady, I think Kenzie logged out. I mean, got
Oh,
disconnected.
all right.
Could
Yeah,
you let her
thank
in?
Thank
Yep.
you.
No problem.
I just put her. Hello, Kenzie. Yeah, you guys got to get to know some people so you can do that, because I'm watching a different screen. So I hope you're okay. We haven't gone too far. Yeah, if you have to leave, always kind of come and petition to get back in, and I'll try to let you do that as soon as I find out. Okay. Anyway, when I have now, what's this about? This is taking the truth values here and putting not on them. So this is an F, this becomes a T, this is a T, this becomes an F. And this is the end result. This is the not P. And what you notice is they're the same. So we say not P is equivalent to P. Okay? And this is just a way that people figured out that would be a nice way to be able to write something down in some kind of order so that other people could quickly understand what something means. It gets a little more complicated with binary, and all of our connectives are either unary or binary. So it's not too bad. But when you have two letters, we have four rows. We have a TT, a TF, an FT, and an FF. Because a statement that has and this, by the way, is read, wow. Yeah, no, it's okay. I thought I just said it wrong. The disjunction of P and Q. Here's an example where we're using this in the source language, and I want to talk about this in the object language. I want to talk about P or Q, but when I brought it up, I said P and Q. Do you see how you could get confused? So this is talking about the thing. This is doing the thing. Okay, so if I have, how do we say P or Q? Well, if both of them are true, I think most people would say the sentence is true. If one of them is true and one of them is false, I think most of us would still say it's true. This is called the inclusive or. We're allowing one sentence to make the whole sentence true. Again, this is one and one. Only if, for an or sentence, only if both parts are false would most people say that the sentence is false. So when people give you an or sentence, 3 of the 4 things they could mean are true. Only one thing is false. And in ordinary discourse, when you and I are talking, we're always acting like what we say is true. Even if we're lying to somebody, we want them to believe it's true. So we never just talk in lies in the sense of saying I'm lying right now, right? We always say something hoping the person believes us. Now, I hope that you guys never lie, of course. But if you do, you act like you're telling the truth. And so what you put into the object from the source, even if you know it's false, you put into the object something that's true because that's what you want people to believe. Well, in math, of course, we only put in true statements because why put in false statements? Because you can't use them, okay? Now, we might assume something's false to do something called an indirect argument, but we'll get to that later. So the truth table for and is a wedge like this. This means P and Q, if you see that. This means P or Q, same kind of a wedge, but upside down. I got Kenzie's out again. I saw her this time. Kenzie, you okay? Kenzie doesn't have her audio. So there she is. I know she doesn't. No, I can't. So if we lose you, Kenzie, just keep coming. I don't know what that is, but I'm reading Michael to everyone. Use the guest with something, whatever. Okay. Can't take time to do all it unless you guys want to say. If you want to interrupt anytime, go ahead, and then we can hear all, hear what you want to say, because then I can hear it too. Anyway, what's the difference between or and? Well, an and sentence is only true when both parts are true. If either part's false or both are false, an and sentence is false. You got to know the difference between the two because they're greatly different. Okay. Now, those are the two main things we use in math, or and. Okay. Now, by the way, if you guys want me to go faster, I can do this in 30 seconds, the whole 30 pages. I hope I'm going at a pace. If you think we're going too slow and you all you know this, then you just tell me that and we'll go faster. Or you can read it on your own and I'll test you over it and you don't have to talk about it at all. We can do all kinds of different things depending on what you guys want to do, which is best for you. Okay. So I'm going at a pace here as if you've never seen this before. Maybe it's too fast, maybe it's too slow, but you got to tell me that later. Like slow down, or this is boring, go faster. Talk about leopards attacking you or something. Or talk about the 30 years you spent with the police department of capturing serial killers that I did. Talk about something interesting. Whatever. Talk about climbing mountains or something. No, we're going to do the math. Now, one of the things you do with more complicated statements, this one says it's not the case that either, because we put either or in with English, it's not the case that not P or not Q. So this is not the case that either not P or not Q. All right. It turns out that that has the same truth table as and, but it's expressed as not and or. But most times, if I would tell you this sentence, you'd wonder what I said. So what we usually do if we see something like this is simplify it to something better, easier, the same way you usually take 3/6 and change it to 1/2. Okay, so now how do you know it's the same? We do a truth table. So in this truth table, again, what you now would do is all this stuff is blank, okay? You fill these out, TF, TF, and TTFF. Then you go to the most inside place, which would be right here, okay? This is going to be, well, that's not the most inside. what you do is find the most inside thing in parentheses. Now, by the way, one of my teaching techniques is to sometimes say things wrong on purpose. Other times I say things wrong accidentally, okay? You're going to have to figure out when I mean to mislead you and when I'm not intending to mislead you. Because all of us make mistakes. So like what I just said was intentional. This looks like the middle, but it's not. What I'm going to do first is the most inside parentheses. So I have a choice. So that's why down here, I said first and first. Now you can't have two firsts really, but the point is it doesn't matter. What I'm going to do is fill this one out right now. How do you fill this one out down here? You look at this column. If it's TFTF, what's not going to be? It's going to be FTFT. Okay? Do I have to go slower? Is that okay? Okay? Now, the other one I have to do first is not P. That's TTFF, so that becomes FFTT. See? Now, I put first down here so that 2 weeks from now, when I go back and look at it, I'll know what I did. Because if you just see this table, you have no idea what I did first. So I find this helpful to put down what I did first. Then now that I've got these figured out, now the OR is the next middle one. So now I do an OR based on these two columns. This column, the first columns, I now look at here. This is OR. I have F and F, but the OR, that's an F. Here I have F and T, that's a T. Here I have a T and an F, that's a T. Here I have a T and a T, that's a T. So if I only had this and not a not in front of it, this would become the truth table. But in this case, I have a not also, so this becomes the last thing I do. So I now take all of these things and turn them around. This becomes T, this becomes F, 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 and this is the truth table for this complicated statement. And what you'll notice is this truth table here is the same as this truth table. Where is it? This one. This one was not used before. This is the one I said was equivalent. I didn't use it in making this one up, but I look over and see what it is. I just did that because I want to remember this line, a column, and this column are identical. And that says we do not distinguish between these two things. So if somebody says this complicated thing to you and they know what they're doing, they're actually just saying P and Q. Okay? So one of the things we try to do in math is simplify statements so that they're more easy to understand without changing their meaning. Okay? So now, there's some of these things are named, like De Morgan's laws. That says if it's not the case at P and Q, then it's either the case at P, not P, or not Q. So when you negate an and, you get an or with both negations. The negation of an and statement is not an and statement, it's an or statement. The negation of an or statement is an and statement. Okay? Now, this here is the first example of reasoning without a truth table. Because once we have some truth tables done, we can then think, we can then reason. Okay? So what I do here to prove this number one is I start out with this left hand right here, and I say, okay, by the rule meta theorem 2 here, that says I can replace this thing by this thing. So I'm going to replace the inside here by the right-hand side up here. And so what you'll see is this not is that not right there. And I see it's getting to be 20 after, by the way. And so I replace that with this. Then I see not here, so I replace that with just the inside, and that proves the theorem. Now, you guys are going to need to study this, so I put down here are some more laws of things that are equivalent and the proofs. And these things take a while. This is called a distributing. We distribute numbers. 3 times 4 plus 5 is 3 times 4 plus 3 times 5. But 3 plus 4 times 5, 3 times 5 plus 4 is not 3 plus 4 times 5 plus 4. That probably is not easy to understand. I'm going to turn off the recording now because I have something more to tell you.